Light is more than just an electromagnetic wave. It brings colors, shapes, shadows, and reflections to the world. How does light make it possible? Certain parts of the electromagnetic spectrum can activate specific proteins in our eyes. This stimulus generates visual experiences in the brain. The part of the electromagnetic spectrum that can produce this sensation is referred to as visible light. Its wavelengths range from approximately 380 to 750 nanometers. Each wavelength corresponds to a specific color. The combination of all wavelengths appears as white. When a ray of light strikes an object, various events may take place. Some light may be transmitted, some may be absorbed, and a portion may be reflected. These occurrences are somewhat affected by the wavelength of the light. At night, all the cats are black. Black is not a color, it is the absence of light. When we turn on the light, white light rays illuminate the object. If it reflects all wavelengths equally, we perceive it as white. If it absorbs all wavelengths except the longest ones, we perceive it as red. If the object reflects only the middle wavelengths, we are likely to perceive it as green, and so on. Color is not a property of an object, but of the light it reflects. If the light source is replaced with a bulb emitting only red light, the object that was red in white light will still appear red. The object that was green in white light will appear black. A green object absorbs all wavelengths except green. When illuminated using red light, it has nothing to reflect. The rule states that light is reflected at the same angle as it arrived. The angle of incidence equals the angle of reflection. When the reflecting surface is smooth, parallel rays stay parallel after reflection. If the reflecting surface is rough, the reflected rays scatter in all directions. This type of reflection is known as diffuse reflection. How do we see our reflection in a mirror? If we find ourselves in complete darkness, we won't see anything until we switch on the light. When light is present, a reflection appears in the mirror. What path must a beam of light follow for us to see our own reflection in the mirror? Light originates from a source, reaches us, and then reflects diffusely in all directions, including towards the mirror. When it hits the mirror, the light bounces back into our eyes. The smooth surface of the mirror ensures that parallel rays remain parallel after reflection, enabling us to see our own reflection clearly. When light transitions from air to water, it changes direction. Light ray bends towards the normal. The angle of incidence exceeds the angle of refraction. This phenomenon occurs when light moves from an optically less dense to an optically denser medium, where light travels at slower speed. Conversely, when light moves from water to air, the path remains the same but in the opposite direction. The angle of incidence is less than the angle of refraction. This rule results in a peculiar boundary phenomenon. When light transitions from an optically denser medium at increasing angles of incidence, at certain angle, the refracted ray will follow the boundary surface between the two media. What happens to the light ray if we slightly increase the angle of incidence? It will be reflected back into the optically denser medium. It will bounce off the boundary surface as if it's a mirror. This phenomenon is known as a total internal reflection. The angle of incidence at which it begins is referred to as the critical angle of total internal reflection. Not all wavelengths bend at the same angle. The shortest wavelength, violet, bends the most. The longest wavelength, red, bends the least. This phenomenon causes white light to separate into rainbow colors after refraction. This occurs in water droplets in the atmosphere when we observe a rainbow in the sky. When white light enters a raindrop at a certain angle, it refracts towards the normal. At this point, white light separates into wavelengths, all the colors of the spectrum. As it approaches the boundary between water and air, the light reflects back via total internal reflection. Upon exiting the water droplet, light refracts once more, this time away from the normal. This additional refraction leads to further separation of light into wavelengths, producing the colors of the rainbow. To witness a rainbow, the angle between the incident light and the light reaching us needs to be 42 degrees. A rainbow is visible only in a specific section of the sky, when the sun located behind us illuminates raindrops in the atmosphere. On a hot asphalt road on a scorching day, in the distance, the asphalt appears to be wet. It's a mirage, an optical illusion. During summer, the sun heats the asphalt so much that a thin layer of hot air forms above it. This layer of hot air acts as an optically less dense medium compared to the slightly cooler air above. When light from the sky reaches this hot air layer, at a certain angle, total internal reflection occurs. Our brain recognizes this as light emitted from the asphalt. We perceive the reflection of the sky on the hot air layer above the asphalt as water on the road. Additionally, this water seems to shimmer due to the movement of hot air that creates variations in the refractive index of light.